name is Dr. Esther Trufan, and in this video, we're going to explore the basics of stoichiometry. Chemical reactions come in a variety of forms. There are decomposition reactions where we start with one reactant and produce multiple products. There's the combination reaction where we start with multiple compounds and we produce one product. There is combustion where we start with a fuel and some kind of oxygen or oxygen-containing material to produce combustion products, which often is carbon dioxide and water. There's double displacement or double replacement or metathesis, where the partners get exchanged, often between two ionic compounds. And there is simple displacement, in which one element is replacing another from its compounds. Now, after we transformed our observations of a chemical reaction into our paper-based chemical equation, it is time to often perform the mathematics of chemical reactions, and that is what we call stoichiometry. This is a chemical equation that gives us the potential to interpret it at the microscopic scale with its smallest constituents, at the macroscopic scale with moles, and also at the macroscopic scale with masses. And of all this, the most important is the mole relationship, because this is where most calculations will be done. The simplest of all stoichiometry problems are the ones where we know the moles of the starting material and we need to calculate the moles of either another starting material or a product. Whenever we know the moles of one reactant and we need to find the moles of the other one, usually the purpose is to determine what amounts we should use for our chemical reactions to be the least wasteful. Because if we match the stoichiometric ratio of our reactants, odds are there will be very little waste. So here we have one example in which we start with 0.34 moles of hydrochloric acid, and the question is asking for the moles of magnesium that will be consumed in this reaction. So we always need to start with our interpretation. 1 mole of magnesium will require 2 moles of hydrochloric acid. So when we write our expression, we start with what is provided in the problem, and that is the 0.34 moles of hydrochloric acid. Our interpretation said for every 2 moles of hydrochloric acid, we will need to consume 1 mole of magnesium. And that is how we write our conversion factor. The moles of hydrochloric acid will need to be on the bottom so that they may cancel out. And then the rest is calculation, which will provide us 0.17 moles of magnesium. It is a simple one-step calculation, and we went from moles of hydrochloric acid to moles of magnesium. There are other options to enter a chemical equation, and that is where one of our ingredients is provided in something other than moles. In order to be able to use the mole ratios from the interpretation, the first step will always have to be use whatever means necessary to convert to moles of the provided material. Here we have 3.0 times 10 to the 21st molecules of hydrogen. Step 1, go from molecules to moles. So we begin with 3.0 times 10 to the 21st molecules of hydrogen. In the first step, we need to get from molecules of hydrogen to moles of hydrogen. And we know Avogadro's number, which tells us 1 mole of anything will contain 6.022 times 10 to the 23rd molecules of that item. And here we have hydrogen moles and hydrogen molecules. So the molecules have been removed. Next, now that we know our moles of hydrogen, we can find out how many moles of magnesium it will require. From the interpretation of our equation, we know 1 mole of magnesium reacts with hydrochloric acid to produce magnesium chloride and 1 mole of hydrogen. So for each 1 mole of hydrogen produced, we consumed 1 mole of magnesium. And with that, the moles of hydrogen cancel, and we have moles of magnesium. At this point, all we have to do is perform the calculation and we will get 5.0 times 10 to the negative third moles of magnesium. The most common thing that we do in the laboratory to set up a chemical equation is to weigh out a starting material amount. Here we start with 0.5 grams of magnesium ribbons. And in the first step, we will need to get to moles of magnesium. That means we need to look up the molar mass of magnesium. And the molar mass of magnesium is 24.3 grams per mole. That means that every 1 mole of magnesium weighs 24.3 grams. Now that we removed the grams and we're at moles of magnesium, we can convert between the moles of magnesium and the desired moles of hydrochloric acid. Based on our interpretation, 1 mole of magnesium reacts with 2 moles of hydrochloric acid. And with that, our final answer will be in moles of hydrochloric acid. The number that goes with it will be 0.04 moles of hydrochloric acid. Another way to enter a problem is if we're using an aqueous solution, we need to know the volume of the solution that we're using, and we need to know the concentration of that solution. The first step, because we usually measure volumes in milliliters in the lab, is to convert our volume from milliliters to liters. Here we start with 5 milliliters. So we're going to use our prefix conversion. 1 milliliter is 10 to the negative third liters, giving us 0.00500 liters of solution. If we know the volume in liters and the molarity, which is moles per liters, we should be able to determine the moles of the solute. So here we start with the volume in liters. And then we multiply it by our molarity. On the bottom, we place the 1 liter. And on the top, we say it is a 3 molar solution. So it contains 3 moles of hydrochloric acid in every 1 liter. The liters cancel, and we have moles of hydrochloric acid. Then we go back to the interpretation of the chemical equation. Every time we consume 2 moles of hydrochloric acid, we also need to consume 1 mole of magnesium. And with that, our moles of hydrochloric acid are canceled out, and we have our final answer. And we get 0.0075 moles of magnesium. Regardless of how we approach problems, the most important thing is to get to that mole-to-mole ratio. If we are provided with a volume and concentration, then we can get to moles. Once we get to moles of one of our ingredients, we can convert to moles of another and then move from there into another direction. So here we have concentration and volume. The 5 milliliters is the same as 0.00500 liters. The 3.2 molar means that we have 3 moles of hydrochloric acid in every 1 liter of solution. And then finally, the last thing that we need is the molar mass of magnesium, which is 24.3 grams per mole. It will be a 3-step process. In step 1, we start with the volume of our solution. We multiply by the concentration. And then once we have moles of hydrochloric acid, we can start converting from hydrochloric acid to magnesium. For every 2 moles of hydrochloric acid consumed, we also consume 1 mole of magnesium. And every 1 mole of magnesium weighs 24.3 grams of magnesium. With this, our moles of hydrochloric acid and our moles of magnesium are canceled out. And all we have to do is complete the calculation. This results in 0.194 grams of magnesium required. For all calculations that involve stoichiometry or a chemical equation for which one amount is known. We need to convert to moles if we are not starting from moles, and then from there use our interpretation of the chemical equations to establish the mole-to-mole ratio between our known amount and our soon-to-be known amounts. The process is relatively straightforward. The important part is always get to that mole ratio. There are many ways to get to it, and there are many ways to convert from that mole calculation to any unit that we are interested in.